Our next speaker, we have a video that we're going to play from Dr. Sundeep Dugar, who's the founder of BlueOakNx Incorporated. He's going to be speaking about the role of mitochondria in primary mitochondrial diseases. He's has a lot of experience in small molecule drug discovery. He's an inventor, publishes widely in research, and he's going to talk about mitochondria, their role in Leigh syndrome and other mitochondrial diseases.
Good morning, everyone. I am sorry I'm not there in person at the global meeting for Leigh syndrome, but it's still a pleasure to join you remotely and perhaps tell you a bit about the work we have been doing related to mitochondria today. I'll touch on the role of mitochondria and perhaps make a connection of more mitochondrial role in Leigh syndrome. Just as a refresher, I know most of you know about the mitochondria, but to remind ourselves, it's the only component in your cell that can make more of itself when needed, fix itself when broken, and get rid of itself when not needed. It's all the process of cellular hormesis. When there's an increased cellular energy demand, it induces biogenesis that is also managed by the mitochondria. And it is affected through both intracellular and extracellular stress that leads to the formation of the permeability transition pores and the resulting destruction in the mitochondria. And this is relevant in disease states and chronic diseases such as Leigh syndrome, where you constantly have the oxidative stress leading to mitochondrial damage. In a way, you can think about this, that there's a competition between inherently cells making more mitochondria and cells losing excessive mitochondria, leading to mitochondrial depletion and reduction in cellular bioenergetics. We'll come back to that a little bit later in the talk to address the idea of mitochondrial biogenesis and mitophagy. Now, of course, mitochondria are fundamental to health. Its purpose is to take in nutrients, turn it into energy, ATP. And as a chemist, I can tell you that the process of ATP that the mitochondria use makes the strongest chemical bond that one can think of by putting two negatively charged molecules together. So think about it, that when you have a south pole of a magnet combining with another south pole of another magnet, that there's an inherent repulsion, but the mitochondria are able to do it. And in doing that, store the energy in ATP, which is then used by all cellular functions. We have about, give or take, 100,000 trillion mitochondria. 25% of a cell volume is mitochondria. And you use about 10 billion or greater ATPs per day. Everything you do, from moving your fingers to nodding your head to walking, uses ATP. It cannot be stored, so hence it has to be produced by cells, every living cell in your body, every second of every day. A healthy person at rest produces their body weight in ATP every day, so perhaps 150 pounds, 160 pounds of ATP. So what essentially I'm saying to you is that this is ubiquitous, fundamental, constant process that goes on in every cell of your body. By the way, except for the red blood cell that has no mitochondria. Every other cell has a mitochondria. And so that really states to you how important the mitochondria are to everyday life and function. It has its own genome, and it's only inherited from the mother. So mitochondria, as you see, has a circular genome, and postulated that it was entered the modern cellular structure through an endosymbiotic event about 2.5 billion years ago. Well, that's a story for another time, but let's get to Leigh syndrome. Now, clinically and genetically, it's heterogeneous. and hence leads to very diverse phenotypic presentation. And sometimes we'll call it the Leigh syndrome spectrum, or LLS. The heterogeneity in part is due to the mitochondrial electron transport chain mutations, or ETC mutations. Now, ETCs are coded by both the nuclear DNA and the mitochondrial DNA, and hence mutations in either genome that is coding for the ETC can result in Leigh syndrome. So it does not have to be only mitochondrial or only nuclear, it could be either. Now, this presents the challenge in this disease that it creates a heteroplasmy, and I'll touch on that briefly in the next few slides. But in a cell, you can have both healthy and diseased mitochondria. So it's not homoplasmic, because if the mutation is homoplasmic, it can lead to an embryonically lethal phenotype. That does not mean homoplasmy leads to embryonical lethality all the time, but it can. But in the case of Leigh syndrome, it's heteroplasmy. So in a cell, you have both healthy and diseased mitochondria. And this degree of heteroplasmy contributes to the complexity and diverse phenotype you see in Leigh syndrome. And this degree also defines the threshold of severity of the disease. Now, here's some work that was done and published about which are the various ETC mutations in Leigh syndrome. So you can see that there's mutations in complex 1, complex 2, 3, 4, and 5. But mostly you see a deficit or a mutation in complex 1. Now, at the top of this picture, you can see that the role of the early complexes 1, 2, 3, and 4 are to simply create a proton gradient between this matrix of the mitochondria and the intermembrane space. And the last ETC, which is ETC5, you see the arrow pointing down, is when this proton gradient comes back into the matrix and makes ATP. So imagine the dysfunction can be both either the mutations in the last one that does not produce enough ATP, or the mutations in the early electron transport chain does not create enough membrane potential to make enough ATP. So if there is a mutation in the early electron transport chain, the mitochondria may not be able to create the membrane potential or the concentration of protons in the intermembrane space to make enough ATP. So that's a dysfunctional mitochondria. It's not that it does not make ATP, it doesn't make enough ATP. So here are the various phenotypes people have put together. So the mitochondrial heteroplasmy, as I mentioned, results in these pathogenic mutations due to pathogenic mutations in either the nuclear DNA or the mitochondrial DNA. Causes the abnormalities in the oxidative phosphorylation capacity of the mitochondria. And then you can see everything from renal dysfunction to hypertrophic cardiomyopathy to ataxia, hypotonia, etc. So what is mitochondrial heteroplasmy? And it is separated from the concept of Mendelian inheritance, where the daughter cells have to be the same as the parent. In this case, when a cell divides, it can divide when it has, say, 40% heteroplasmy to give two daughter cells, and one can have only 20%, the other may have 60% heteroplasmy. When that 60% daughter cell divides to the next generation, it can create a cell with now 80% heteroplasmy. So what the idea here is that as these cells divide, the functional and dysfunctional mitochondria are not equally distributed in the daughter cells. And that excessive dysfunctional mitochondria then in subsequent generation leads to the clinical manifestation we see. So, and this leads to the accumulation of depolarization and ROS-generated mitochondria, attenuated ATP production, as I'd mentioned earlier, and then leads to improper cellular metabolism and signaling pathways. Because in these daughter cells, suddenly there's not enough bioenergetic. But it also leads to decreased mitophagy because the cells don't have enough energy to now invest in getting rid of these dysfunctional mitochondria, so they accumulate. So what are then the challenge in Leigh syndrome and what are the current efforts people are looking at? So, of course, we all know about the phenotypic and genotypic variability associated with Leigh syndrome. And so people are looking to develop treatments to increase ATP production, increase mitochondrial biogenesis, target dysfunctional mitochondria for degradation. And all this is to improve mitochondrial health in cells and tissues that are impacted by the disease. So a very logical approach. The other options people are looking at are mitochondrial replacement therapy, gene therapy, hypoxia, and we won't have time to go into the details here, but that induces mitochondrial stress and promotes mitochondrial biogenesis. Then there are pharmacological treatments, including diet, which people are looking to do to increase mitochondrial biogenesis or autophagy to prevent oxidative damage. They're targeting targets such as AMP kinase, sirtuin-1, the mTORC-C1, PGC1 alpha. They're talking about caloric restrictions, even supplements such as CoQ10, idebenone, et cetera, are in evaluation for people to study. But most are in preclinical or clinical trials, and some of them showing conflicting results in these trials. So there's really not been a very clear outcome of these studies to say that there is an intervention that is could be available near term. But if one were to think about this, that if you want to increase mitochondrial activity, mitochondrial biogenesis, induce mitophagy, one of the best ways to do is through the mechanisms of exercise. So just stay with me for a moment. Exercise is the most natural way we know of improving mitochondrial function, protecting mitochondria from damage, and inducing new mitochondria through biogenesis. And those are the things we are wanting in these patients. And exercise is the one great way to do it. Now, however, while exercise can have positive impact on the disease and for managing symptoms of Leigh syndrome, as it can improve and will improve mitochondrial function, but the common symptom of Leigh syndrome is exercise intolerance or inability to exercise. So you now have a conflicting issue where exercise will help the patients, but they unfortunately are not able to do it. Over the years, our research has been focused on trying to identify the process that is induced pharmacologically when you exercise that leads to these mitochondrial benefits. And that has led to the identification of a novel steroid that is made by the mitochondria during exercise. And we have studied this steroid. We have detected it in humans. And this steroid initiates the pleiotropic outcomes of exercise. That includes mitochondrial biogenesis and protecting the mitochondria from damage, and including the downstream transcriptional processes that are induced when you exercise. And what we have found also is that minus epicatechin alone by itself mimics the pharmacology of this novel mitochondrial steroid that are expressed during exercise. So mitochondria activity is enhanced by epicatechin, and it also induces the molecular and transcriptional pathways that are associated with exercise. It also increases mitochondrial biogenesis, crystalline density, where ATP is made within each mitochondria, which results in enhanced ATP synthetic capacity. And this activity of minus epicatechin again correlates with the activity of the steroid. It also induces expression of antioxidation enzymes such as superoxide dismutase, catalase, which benefits surrounding tissue and reduces oxidative stress and injury. And also, significantly, it protects the mitochondria from damage by inhibiting the formation of permeability transition pores induced by oxidation state. And both epicatechin and the steroid do this. So, in conclusion, what we have been able to find is that exercise induces a novel new steroid, which does the purpose of enhancing mitochondrial function, concentration, and protects the mitochondria. And minus epicatechin is a natural structural congener of this steroid and mimics its pharmacological activity. If this is true, then one can anticipate or expect that minus epicatechin can give lay patients the benefit of exercise even when they have exercise intolerance or have unable to exercise. This then can result in the pleiotropic responses expected of exercise and improve mitochondrial function and levels. And most importantly, it can also induce mitophagy, that is getting rid of the dysfunctional or damaged mitochondria that is accumulating in the cells, and that can help maintain healthy mitochondria and reduce oxidative stress. At the end, when you have an improved mitochondrial function, you can improve endurance, reduce fatigue, perhaps affect disease progression, improve aerobic capacity, and overall improve quality of life. So in essence, if the manifestation of the pathology or pathophysiology of Leigh syndrome is associated with dysfunctional, depleted mitochondria or increased accumulation of damaged mitochondria, and exercise can be of help to these patients, then the correlation of minus epicatechin to this steroid expressed during exercise can be a potential path. The idea would be improving endurance, reducing fatigue, potentially slowing progression, improving aerobic capacity, improving quality of life, etc., and all through the basis of improved mitochondrial function. With that, I want to thank you for your time and your attention. Unfortunately, since I'm not live, I would not be able to take any questions, but perhaps there will be another time to do so. Thank you much.
Well, thank you, Dr. Dugar. That was some great background on the importance of mitochondria and how different mutations drive disease and the ways you're trying to overcome these energy challenges.